So I broke this unit up into two different topics. So I'm going to be flipping back to the same PowerPoint because the PowerPoint uses both portions of it. So this first unit that we're going to go over is phase changes. So we'll be going, you know what phase change is, right? Liquid to gas, gas to solid. We'll be going over that. So this first test is only going to be going over the simple phase changes. Should be relatively easy. The second unit, we're then going to go into the math behind it. But it does mean that I'm going to be switching and skipping some portions of PowerPoints. And also, I'll be reusing some of the terminology on both tests. Alright, phase changes. So the water cycle is a very good indication. We have evaporation, where the liquid water is turning into a gas. We have condensation, where the gas is turning into little liquid droplets. Also, we have precipitation, where the more dispersed liquid is turning into liquid drops. That comes down, turns into liquid, back into liquid. We also have ice that can form. So thermal energy. Thermal energy, also known as heat energy, is the total energy of all the particles. It's the kinetic energy plus the potential energy. All matter has thermal energy. So if y'all remember, what's the definition of temperature? Anyone remember the average kinetic energy? So temperature is the average kinetic energy of all the particles. Thermal energy is the total energy. So temperature is on the average, whereas thermal energy is the total. So, for example, so if you take boiling hot water, 100 degrees Celsius, if you were to take a single tiny drop and put it on your hand, versus someone taking a gallon of boiling hot water and pouring it into your face, which is going to hurt worse? The single little drop of boiling water or a gallon of it being thrown at you? A gallon. So they're at the same temperature. So temperature is more of a measure on the average, whereas thermal accounts to the total. So there's a lot more energy to do harm to you in a gallon than there is in a tiny drop. In chemistry, temperature is important, but sometimes we need to know the entire total energy. In which case, the entire total energy depends on how much you have, whether you have a gallon of it or a single drop. So if you've never had a physics like class, or I think science should have talked about this, 8th grade science, we have potential energy and kinetic energy. Potential energy is stored energy. This could be stored in the bonds between atoms. And we have kinetic energy, which is the energy of motion. All atoms are moving and vibrating unless at absolute zero, and you can never reach absolute zero. So kinetic energy, in reference to chemistry, includes the actual motion of the atoms moving, and also how much they're vibrating. So in a solid, the atoms don't tend to move around, but they still vibrate back and forth. So all forms of energy fall under these two categories. Whether it's the potential energy, which is stored in due to its position or configuration. There's also gravitational, but we don't concern ourselves with gravity in this class. There's also kinetic, which is energy motion. This is due to the motion of waves, electron, atoms, molecules, and substances. We also have something called heat. Heat is the amount of thermal energy that is transferred to an object or area. So this is very different from temperature. Temperature, again, is average kinetic energy. Heat is a measure of true energy. Heat is a measure of the thermal energy that is transferred. A lot of places you'll see that thermal energy and heat energy are the same words. They mean the same thing. So instead of saying thermal energy, you might see me slip up and call it heat energy. I try to be consistent when teaching a subject, but for example, in IPC and physics, we usually call, or at least in IPC, I call it heat energy. And in chemistry, we try to stick with thermal because we also have something called just heat by itself. So there's heat energy, which is thermal energy, and then there's heat. Heat is the transfer of thermal energy. So I'm going to try to be consistent in this class and just call it thermal energy. But heat by itself is the transfer of that energy. So, for example, in cooking, when you're cooking an egg, if you do it over a gas oven, the heat will go from, so energy is being released from the chemical bonds as you burn the gas, and that heat is being transferred from the gas molecules to the stove, or to the frying pan. If you have electric, then it's going from the actual stove to the frying pan. From the frying pan, the heat then transfers to the egg, heating it up. So we have 4 phases of matter: solid, liquid, gas, and plasma. We're going to be ignoring plasma. We only really have 3 in this class that we'll be worrying about: solid, liquid, and gas. You can ignore plasma. So solid, the total motion is the slowest out of the 3. As the particles speed up and are able to slip past each other, they become a liquid. And then they get enough speed, they can start moving freely into the container and become a gas. So in a solid, the atoms are packed the closest, and they don't have very much energy. They have the least energy out of the 3. In a liquid, the atoms are packed close together, but not as close as when they're solid, and they have moderate energy when it's a liquid. In a gas, the atoms are extremely far apart, and there's a lot of energy. So what is a phase change? It is a change from one state of a matter to another. So from either solid, liquid, gas into another phase, such as solid, liquid, or gas. Again, we'll be ignoring plasma because we don't deal with plasma in this class. Do y'all know what plasma is? Name the most common plasma thing. What? No, that's a wrong type of plasma. That's the liquid that your blood's in. Have you ever heard of a plasma torch? Whenever I think plasma, the first thing that comes to mind is the sun. The sun is a plasma. If you want to write this down, again, I'm not covering plasma, but if you want to write this down, plasma is when a material becomes so hot that the electrons no longer bond to the atom. So it's so hot that the electrons are able to fly off the atom. At that point, it's called a plasma. So again, we have solids. The atoms are bound together. When you heat it up, it becomes a liquid, and atoms are able to flow past each other, but are still bound together. If you continue to heat it up, the atoms are able, or molecules are able to escape and no longer become bound together. That's called a gas. And if you continue to heat up that gas, the electrons will eventually be able to fly away from it. And in this class, we're going to be assuming that the electrons are still attached to the atom because it's very complicated. It's basically doing chemistry in the sun. It's not something we encounter in a lab. We can create plasma on Earth. We have a plasma torch in which it gets so hot that the electrons are coming off. Usually, in order to create a plasma torch, we have to run high voltage through it to strip the electrons off. Another thing is lightning. When lightning strikes, the air heats up so hot that the electrons get blown off. It's not exactly on temperature alone. But anyway, phase changes are physical changes because it only affects the physical appearance and not the chemical makeup. And if you can remember I said that during this class, when I teach something, we're going to be using it throughout the year usually. Physical changes are changes that only affect the appearance and are reversible. So if you can reverse something, such as ice melting, that's a phase change, is a physical change because you can put it back into the freezer and turn it back into ice. So if it's reversible, that usually indicates that it's a physical change. So what happens during a phase change? By the way, out of curiosity, if I were to put ice on a stove and start heating it up, what happens to its temperature of ice? It does what? Leave? What? It raises, so the temperature of ice increases as you heat it up? It wouldn't be ice, so that's correct. But what happens to the temperature of the remaining ice? So if I have a big chunk of ice, what happens to the temperature of ice as I'm heating it up? We'll see in a... Yes. My point is the ice doesn't change temperature. It only changes phases. That's my point, was that the ice has to be at 0 degrees Celsius. It has to stay at 0. Because if it's not at 0, it's no longer ice. So during a phase change, heat energy is either absorbed or released. And again, so even here it does it. Heat energy and thermal energy are interchangeable words. So you'll see it throughout out. Heat by itself is just a transfer of heat energy or thermal energy. The heat energy and thermal energy are the exact same thing. There's no difference between them. The word heat just refers to the transfer of thermal energy. So either heat is absorbed or released. So thermal energy is either absorbed or released during the phase change. Note, let's go back. Thermal energy refers to the total energy of all particles. This not only includes the kinetic energy, it also includes the potential energy. So if you are absorbing heat energy, that doesn't mean your temperature is increasing because your potential energy can increase too. So in the case of ice, remember temperature is just average kinetic energy. So if you heat up ice, the ice temperature, like you said, Lucas, doesn't change. So that means the kinetic energy must not be changing. So what must be changing? Potential energy. I can get thermal energy changing. But thermal energy is total kinetic and potential, was what I'm getting at. So when you heat up ice, you're changing the potential energy of the ice molecules. You're changing its configuration. So heat energy is released as molecules slow down and move together. So if they slow down, this is kinetic energy. So we're changing multiple things too. If the atoms slow down, we're also changing kinetic energy, which would be temperature. As heat energy is absorbed and molecules speed up and expand, if you're speeding up, you're changing temperature, kinetic energy. As they expand, you're also increasing potential energy. So energy is either absorbed or released during a phase change. Endothermic, the system absorbs energy from its surroundings, so energy goes in. I memorize this as endo, the en is in, so endo means into. So energy goes into the system. So baking bread, producing sugar by photosynthesis, evaporation of water. So when water evaporates, it's absorbing heat from the surroundings and it's absorbing energy into the water. So the water has to increase in energy. So energy is going into the water molecules. So this is endothermic. Exothermic, I remember exo being exit. So the energy exits. So think of exits. So energy exits the molecule. So energy goes out. So the system releases energy to its surroundings. Energy goes out. So making ice cubes. Whenever water freezes, it has to lose some of that thermal energy. So that means that some of the thermal energy is leaving and going out into the surroundings. So freezing water is exothermic. And if I go too fast, tell me to go back. So how to recognize a phase change? Measure the temperature of a substance as it's heated or cooled. Temperature of a substance does not change during a phase change. I don't think I'll have it set up tomorrow. The next day, though, I want to do an experiment. Again, I really wish I had my thermal thermometer, but we're going to take some ice and we're going to heat it up and measure its temperature over time. The phase change during a phase change, temperature does not change. What we're doing is changing the potential energy of the molecules. We're changing their configuration around. Some molecules might be heated and go faster, but overall, since temperature is kinetic energy, average kinetic energy, whenever we're adding heat to ice, we're not actually increasing the kinetic energy. What we're doing is increasing the potential energy of the molecule by allowing it to move more faster. Yes, some of the molecules closer to the heat source are going to speed up because we can't heat up the entire ice at the same time. But what we're doing is giving it more potential energy. So to go from solid to liquid is called melting. To go from liquid to solid is called freezing. To go liquid to gas is called vaporization, not evaporation. I will get here in a second. There's a difference between vaporization and evaporation. So to go from liquid to gas is vaporization. to go from gas to liquid is condensation. You might never heard of this, but solid to gas is sublimation, and gas to solid is deposition. We really don't, so we don't use plasma, but they go from gas to plasma is ionization, and plasma to gas is recombination. You don't have to remember the plasma portion. It's not on the test at all. Only these three. So, can anyone think of an example of sublimation? When does something that's solid turn into a gas directly without ever going into a liquid? So, can y'all think of any solids that go directly to a gas and never become a liquid? Have you ever had a block of dry ice? Have you ever seen liquid dry ice? So, have you ever seen dry ice or seen a video of it at least? What happens to it as it warms up? Or as it undergoes a phase change? It turns into fog. It never turns into a liquid. In order for it to be a liquid, it requires a lot of pressure. And at atmospheric pressure, it can't exist as a liquid. Because it's at negative 200 degrees Fahrenheit. Enough to cause frostbite very quickly. That temperature. So temperature of dry ice. So if it's a solid, it's negative 78 Celsius. So negative 78 Celsius to Fahrenheit is negative 108.4. So it's less than negative 100 degrees Fahrenheit. You don't want to touch it because that could really quickly cause frostbite. Again, as you heat it up, just like if you put ice on a stove, it makes it turn into a liquid. We'll learn a little later on when we talk about phase change diagrams. We'll see. So in order for something to be a liquid, not only does that depend on temperature, it depends on pressure too. So if you were to remove, for example, your blood's a liquid, right? If you were to step in a vacuum chamber, your blood will start boiling and turning into a gas. Because there's not enough pressure to keep it as a liquid. Yes, if you paid attention to the scuba diver, the gas can be dissolved into the liquid. It's not really a phase change here because it's still a gas in the liquid, but still, as pressure drops, liquids come out. Liquids also turn into gases at different pressures. Anyway, we'd say that CO2 sublimes or undergoes sublimation, and that means that it turns into a solid to a gas. So as heat is added or taken, and this is important, remember that heat is not temperature. Heat is thermal energy or heat energy. It's not temperature. So as heat is added or taken away, matter changes its state or phase. So if we were to add heat to a solid, it would eventually melt. If we keep adding heat, it would eventually vaporize or undergo vaporization and turn into a gas. We can also remove heat and it can, from a gas and it'll condensate or undergo condensation. We can remove heat from a liquid, causing it to freeze or undergo freezing. Some materials, based on pressure, can go directly from a solid to gas. That's called sublimation. And some of them can skip the liquid phase and go from a gas to a solid, called deposition. You'll need to memorize each of these terms, this entire diagram. You need to know if I say something sublimes or undergoes sublimation, I'm referring to it going from a solid to a gas. If I say that a gas deposits itself onto a surface, you need to understand that a gas is undergoing deposition and going straight to a solid without being a liquid. If I say that a gas condensates onto the surface of a liquid, that refers to it going the phase change from a gas to a liquid. You might have noticed that so again, a state of matter depends on temperature and pressure. As the temperature in the morning falls, or better yet, you take something out of the refrigerator. Let's say you take some milk out of the refrigerator and leave it on the counter. So there are water vapor, so water in the form of a gas, in the air. As it gets close to the cold gallon of milk or whatever, the temperature drops and it'll start condensating on the surface of the milk jug. And you'll see liquid droplets of water on the surface of it. If you go to a restaurant, you might get a glass with ice. As the water vapor from the air gets near the glass, it'll start condensating on the side of the container. You'll see little beads of liquid water on the side. That's because the temperature decreased, so heat energy was removed from the air as it got near the liquid or the glass of ice. So if you're going from a solid to liquid to gas, so if you're melting then evaporating, this is endothermic. So in order to go from a solid to a liquid, you need to absorb energy into the molecule. So into, it refers to endothermic. Again, to go from a liquid to a gas, imagine the particles are going to need to speed up or spread apart. So they're going to need to absorb some energy to do that. And going in reverse is exothermic. So going from a gas to a liquid, it's going to have to release and give up some of its energy. To go from a liquid to a solid or freeze, you're going to have to give up some of your energy, and that means the energy exits the system. For sublimation, going from a solid to a gas, again, in order for it to go to a gas, it's going to need to absorb some energy into it, so that's endothermic. Going from a gas to a solid, which is deposition, it's going to have to release some energy, so it's going to be exothermic. Oh, let me explain this. I'll do it on the next slide. Everyone good? So when I say that, so temperature is average kinetic energy. Kinetic energy is the energy of motion. There are two types of motion an atom can do, or a molecule can do. It can vibrate back in place, or it can move freely, right? Or some combination of the two. When an object is a solid, the atom can't move anywhere, but it can vibrate really fast back and forth. So as you're heating it up, the kinetic energy is going to stay the same during a solid to liquid. But you have the molecule still speeding up and getting faster. What's going on is it's going from vibrating really fast to moving really fast, right? So the molecules are speeding up, but the kinetic energy is staying the same. That's because they are bouncing really fast back and forth. But as you increase it, you're going to have it start moving more freely. So some of the vibrations turn into actual speed. So molecules speed up and move farther apart and absorb heat energy. This is endothermic. And I know this PowerPoint repeats itself over and over and over again to really hammer in this principle. So during a liquid to solid, molecules slow down and move closer together. When they come closer together, they can't move anywhere, so they're just going to vibrate back and forth. They also release and give up heat energy, and this is exothermic. If y'all need me to go back, tell me. This is basically just a repeat of everything again. So, another word for vaporization, and I will allow you to use it, is boiling. So if you boil water, it's the same thing as vaporizing water. I will count both of them. Yeah. It occurs at the boiling point of matter. So molecules speed up and move farther apart. They have to absorb heat energy. Absorbing is endothermic. We do. Because boiling is layman term, while vaporization is more scientific. So vaporization. That's 5 syllables. Boiling. 5 syllables versus 2 syllables. That's usually some of the reasons. That's probably the principal reason why we say boiling often versus vaporization. So here's an important thing. Evaporization is different than vaporization. I would definitely write this down. Evaporation is when a liquid becomes a gas at the surface of a liquid, and it can occur at any temperature. Vaporization only occurs at the boiling point. So this is a very key distinction between evaporization and vaporization. So, like in the freezing cold morning, you could see a fog, but it's definitely not boiling outside because it's freezing cold. This fog is due to evaporization. To explain it, I'll wait until y'all. Everyone good with the? So remember that temperature is average kinetic energy. Keyword is average. So we have particles that are moving really fast. We have particles that are moving slow. We have particles moving with a medium speed. So they all have, and the length of the line here is, I'm trying to allocate the speed. So the temperature of this liquid is the average kinetic energy of all the particles. They all have wildly different speeds and everything. Occasionally, a particle will get to the very top and have enough speed to escape the liquid. So occasionally, like if you have a glass of water, one of the particles has enough kinetic energy to escape. So evaporization occurs when one of the faster high kinetic energy molecules gets to surface and is able to escape. Its kinetic energy is high enough to break surface tension. So vaporization occurs when one of the faster or high kinetic energy molecules get to the surface and is able to escape. Whereas if you were to heat this up, you're increasing the kinetic energy of all the particles. Everyone good? Here's the code word for the day. Condensation is when molecules slow down and move closer together and release heat energy. Sublimation. Y'all need me to go back? Sublimation is when molecules speed up and move farther apart and absorb heat energy. So here's a block of dry ice. You don't see any liquid near it. That's why they call it dry. It's because CO2, dry ice, if you didn't know, is carbon dioxide, CO2. If you were to breathe out and then reduce that your breath down to like negative 150 degrees, it'll turn into dry ice. But as you put it into any temperature above negative 100 degrees Fahrenheit, it will start turning into a gas, a solid. Here we have deposition. Molecules slow down and move closer together and release heat energy. So the gas actually turns directly into a solid. I don't know what this is. It's zoomed in. That's 1 micrometer. I think your hair is, 60 micrometers? So this is like 1/60th the width of a hair. Probably mold or... I don't know what that is. I know iodine sulfide? I don't know. There's one chemical. How much time do we have? We have 10 minutes. Yeah, I was just looking at the time, sorry. So, graphing a phase change, I might do a lab tomorrow, because I want to reproduce this graph. So I'm either doing the lab tomorrow or the next day. So plan for a lab tomorrow. I should have enough time to do the lab tomorrow. Because if we were to graph the temperature of a material as we heat it up, so we keep the amount of heat energy going into the system constant, we can see that while it's a solid, temperature is changing, but the moment it starts melting, the temperature no longer changes. So this is of water. So water is as you heat up the ice stays at 0 degrees until it's fully turned into a liquid. So as you have some ice water as you're melting ice, it'll turn into ice water. The temperature isn't going to change until all the ice is gone. At which point you start heating up the liquid. The temperature of the liquid will then go from 0 degrees Celsius to 100 degrees. At the moment it reaches the boiling point, you are unable to increase the temperature of the water anymore. So when you have boiling hot water, it's at 100 degrees exactly. There is some real world issues with this statement. For example, you're heating up from the bottom, and the top is exposed to air. What happens if you have 100-degree hot boiling water and you just leave it? It'll eventually cool down because some of the energy is being lost to the surroundings. So if you're heating up water, the top is exposed to the surroundings, so it's losing some energy from the air. And you're only heating up the bottom, so it's not quite 100% true because of reality. But if we have a perfect system to where we can close up the container and ensure that none of the energy is lost to the surroundings, we would see this graph exactly. And I think I'm going to try to set it up tomorrow and have us actually graph and prove that during a temperature change, or during a phase change, temperature doesn't change. So the slanted portions of the graph refer to temperature change. So we can see we're plotting time and temperature. So during the bottom portion, when it's the coldest, when the temperature is the lowest, is when it's a solid. So during the flat portions, temperature is not changing. This is a phase change. So when temperature is changing, kinetic energy is the only thing changing. Whenever a phase is changing, only potential energy is changing. So slanted portions refer to temperature changing. It's a single phase. It's either heating up or cooling down, and only kinetic energy is changing. During the flat portions, temperature is not changing, so it's undergoing a phase change, and potential energy is changing. And remember that thermal energy or heat energy is the sum of these two things. So while we're increasing or adding heat energy, we're either going to be changing the kinetic energy or the potential energy. During temperature changes, the kinetic energy is changing. During phase changes, potential energy is changing. So a plateau, so if you see a graph like this, the plateau tells you where the temperature has changed. So either the thermometer is off, or this is salt water, or not pure water. Because if we can read it here, we can tell that the melting point of the substance is about negative 10 to negative 15 degrees Celsius. We know that water is 0 degrees Celsius, so this isn't pure water. Our temperature, our thermometer is broken. Melting point is the temperature at which a solid changes into a liquid. Boiling point is the temperature at which a liquid changes into a gas. And by the way, we can say that melting point is the same thing as freezing point. It doesn't matter what direction it's going to, it's the same temperature. So things that water melts at 0 degrees Celsius. It also means that water freezes at 0 degrees Celsius. So a melting point or freezing point is the same temperature. Boiling point and condensation point is the same temperature. So melting point refers to the temperature at which a solid changes into a liquid. Boiling point means the temperature at which a liquid changes into a gas. And freezing point is the same thing as melting point. It's the same temperature. It's the same temperature when it's the same temperature when a liquid turns into a solid as a solid turns into a liquid. So in summary, We'll go into later calories and actually next unit. So next unit will actually calculate heat energies, how they go into it. But yeah, tomorrow just go ahead and plan. We're going to be doing the lab tomorrow. Hmm? Yes. 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 If you were to heat up that seat, eventually the plastic will start melting. Oh yeah. What do you think would happen to the wood as we start heating it up? It would probably would sublime at one point or catch on fire. So we wouldn't say that it sublimes whenever you burn it and it turns to a gas. But if you were to remove oxygen from the room, there's no way for it to burn. Because without oxygen, there is no burning. It would probably either liquefy or sublime. I don't know the chemistry of whether or not wood has a melting point or a sublimation point. uh, now that I'm thinking about it, it probably has a deterioration point to where the chemical actually changes and breaks apart. It probably can only exist as a solid. Yeah, and depending on pressure and yeah.